Okay, now we're going to look at a proof as to why cosecant and secant have this range we were just talking about. Now remember, cosecant and secant behave exactly the same, so the proof for cosecant is the same as the proof for secant. Again, here's secant, here's cosecant. The upside down u's and the right side up u's are going to have the same y values at their vertexes. We can call them vertexes, regardless of whether it's secant or cosecant. So this proof will work the same for both. So we've already shown, we can see on the graph that one of the vertices you could say, is going to have a y value of -1. So we're going to go ahead and plug that in for the cosecant of bx plus c, and that will give us the y value of that vertex. But we don't know for right now whether or not that's going to be the bottom or the top of the vertex. Now, A is going to be positive in this case. It's going to be a similar proof as we did for sine and cosine. So that might allude to the fact that it's probably going to be the bottom. Remember, A usually flips the graph. When A is positive, I just want to go back to the graph. When A is positive, let's reset this. When A is positive, that -1, the upside down u's are going to be on the bottom of the graph, right? The A is just going to make those upside u's go down. The only way it flips to where these points become, when the upside down u's become right side up u's and then become +1, is when A becomes negative, okay? So right now we're looking at A as positive, so that should help you kind of understand what's going on with the proof. So we plug in -1 for this, we get -A plus D. Switch them and we get D minus A. Since A is positive, we know that the absolute value of A is equal to A, so we can replace A with absolute value of A. This will give us our bottom vertex of D minus absolute value of A. It will give us one of these down here. Okay? Alright, next up, if A is positive, add sine, it should be cosecant. If A is positive, let's look at what happens if we have that y value of the top vertex of 1. Now again, just assuming, we're just going to say this is a vertex right now, and we're going to prove it's the top one. So A times 1 is A. I'm going to have plus D over here. Flip them, and then you get D plus A. And then we've just shown that A is equal to absolute value of A. So D plus absolute value will indeed give us the top vertex. It'll give us the middle of the graph plus the absolute value of A. Okay, so what if A is negative? Well, if A is negative, again, we're going to plug in -1 for, we know that's going to be the y value of one of our vertices. That's going to become -A plus D. We're going to flip that and become D minus A, but since A is negative, -A is equal to the absolute value of A, and therefore we can replace -A with absolute value of A. This tells us that this will give us the top vertex now. When A is negative, we have D plus absolute value of A. That will give us the top vertex. And as you can see, like I said before, if you make A negative, the bottoms go to the top and the tops go to the bottom. And then your D value is still in the middle, but now it becomes D plus absolute value of A, and that will now be your top vertex, which is what TVX stands for. When A is negative, and we plug in +1, we've done this proof enough. We've seen that A is equal to absolute value of -A, and therefore we get the bottom vertex is D minus absolute value of A. Again, we can see that here. D minus absolute value of A gives us down here, and that's because the graph has been flipped. What was at +1 has now become down to -1. You can kind of see it happen if you move it. In fact, I'll do the auto function here, and you can kind of see what happens when A becomes negative. It flips, right? And the top vertex becomes the bottom and vice versa. Okay, so the bottom vertex is D minus absolute value of A. Either way, you can see when A is positive, the bottom vertex is D minus absolute value of A. And when A is negative, it's also D minus absolute value of A. And whether or not A is negative or positive, the top vertex is going to be D plus absolute value of A. So what does that mean? It will always be that way, and therefore the range will always be from -infinity, comma, D minus absolute value of A bracket to bracket D plus absolute value of A, comma, infinity. D minus absolute value of A representing the bottom vertex, and by bottom vertex I mean these are here, these points right here, and then top vertex is going to be d plus absolute value of a, and by top vertex I mean these up here, d plus absolute value of a. These vertices on these so-called parabolas. That will give us the range for any secant or cosecant function regardless of a, b, c, and d. Okay, so that's it for our proof of the range of secant and cosecant. I could go into a more thorough proof using calculus, but for right now this will suffice for showing why the range is the way that it is for secant and cosecant. If you have any other questions about this, let me know.